Hello everybody, my name is Jason. I'm a second year engineering science student at the University of Toronto, and today I'll be talking about the course ESC180 Introduction to Computer Programming. Today is December 20th, 2021. I would normally be studying for an exam right now, but because all my exams were canceled due to COVID, here I am. I will, however, be talking about two of the final exam questions that were part of the final exam for ESC 180. Um, I guess there's that. But anyways, let's just get started. So what exactly is ESC 180? It's a year one fall course in the engineering science program at U of T. It's compulsory for all Eng students. And when I took the course in fall of 2020, I had Professor Michael Guerzhoy. So the main course topics, this course really focuses on Python programming. So it's the only language that's covered. I mean, you do a little bit of like HTML, not really, but it's just to sort of understand how you can use Python um, to, look at like HTML elements and stuff like that, but nothing like in depth. So we talk about variable types. It's really like you're not expected to have any programming knowledge, so you really start from the ground up. Talk about conditionals, functions, loops, strings, lists and slicing, aliasing and mutability, which is sort of a more advanced concept, shallow versus deep copies, tuples and dictionaries, so very basic data structures. And then we talk about algorithmic problem solving, so generating combinations or permutations, which um, we will see in these final exam questions I'm going to cover. Talk about time complexity or big O notation, so looking at runtime complexity and how it changes asymptotically. We also talk about sorting algorithms, so we go through a bunch. I've just listed a few: bubble sort, selection sort. We also cover like bucket sort, I believe, and a few other ones. So as I mentioned, I'll be covering two exam questions from the final exam I took in this course. They were from the 2020 final exam. They were the last two questions, question 4 and question 5. I wrote this exam a little over a year ago on December 17th, 2020. The topics that these questions covered were permutations, list manipulation, recursion, and very importantly, Python's eval function, which is really funny to me because when I wrote this exam, I actually had no recollection of Python's eval function, and so I struggled a lot with these questions. But you'll see it makes the question doable. But I also chose these two questions because they're extremely related. So as you'll see. So this is question 4. It looks very long, but basically it's asking us to write a function that takes in two inputs. The first input is a list called nums, and it contains three numbers. And the second input is called target, and it's just a number. And what our function should output is it should return a string that contains an arithmetic expression that uses all the numbers in the list, nums, once, and the arithmetic expression should evaluate to target. And we should assume that the task is possible without using parentheses. And the example given is if we give nums to be 3, 1, 2, and we want our target to be 7, the function could return 2 times 3 plus 1, or it could return 1 plus 2 times 3. And either output would be fine. So first of all, we should notice that if we have just three numbers, each expression should have the form num1, operation 1, num2, operation 2, num3. We can't really get anything else. And so num1, num2, num3 are just numbers that are given in the list nums. And operation 1 and operation 2 are just arithmetic operations, which include addition, subtraction, multiplication, division. And note that for this question, we're not going to use a subtraction sign, as an arbitrary negative sign. So for example, we're not going to put like an operation before num1. We're just going to take all of our numbers to be as they're given in the problem. And so the general algorithmic approach to solving this problem would be to generate all possible expressions of the above form, because we're given num1, num2, num3, but we can change the order, and we can also change what operations we use. So that would be to generate all possible combinations of these expressions, evaluate them using Python's eval function, and check if they evaluate to the target that we want. And if it does evaluate to the target, then we should return that specific expression. So this is definitely a permutation problem, because given a list of three numbers, we can permute them in different ways for these numbers, num1, num2, and num3. And for our operations, we can also permute given our four arithmetic operations. So this is the code for the solution, and this solution is written by Professor Guerzhoy, so credit to him. But basically, as you can see, we essentially have 5 nested for loops. And it's doing exactly what I explained in the last slide, which is it's creating a string which contains num1 followed by operation 1, num2 followed by operation 2, and then num3. And we have 5 nested for loops because we need to permute for all the different possible combinations. However, it's important to note that when we're looping through the numbers n1, n2, and n3, we need to check that they're not the same. So, for example, this if condition in line 5, we need to check that n2 is not equal to n1, because if it is, then we've used the same number twice, and that's no good. We should only use each number once. And likewise, in line 8, we're checking if n3 is equal to n1 or n2. And if it is, we should also skip that case because we need to make sure each number is only used once. And some basic permutation math will tell you that given 3 numbers, you can permute them in 3 factorial ways. So there be 6 different combinations for n1, n2, n3, or permutations, I should say, sorry. And then for the operations, it should just be, given that we have 4 operations, it would be 4 to the power of 2, so 16 different permutations there. Anyways, once we have created our expression, we should use the Python eval function, and if it's equal to the target, we should return it. If not, we should continue through this loop. And again, we're assuming that this task is possible, which is why we don't have another exit condition. So that was relatively simple. Now we need to write a function getTarget, which again takes in 2 inputs, nums and target, and it should return a string that contains an arithmetic expression that uses all the numbers in the list nums once and results in target. But this time we can use an expression that contains parentheses. It's also important to note that there's no limitation to how many numbers are in the list nums. So in the example given, if we use getTarget on the input 1567 and we want a target of 21, it could return 6 divided by 1 minus 5 over 7, all in parentheses. So this task seems a lot harder, but in general, we still sort of want to follow the same procedure, which is to generate a bunch of expressions, in fact, all possible expressions, and then evaluate them to see if they get the target and return one that does. So how are we going to do that, and how are we going to do that with parentheses? Well, what we should note first is that obviously, like in the last example, we have a very specific structure to our expression, which is just alternating numbers and operations until we get to the final number. So we'll have n minus 1 operations and n numbers, where n is the length of the input list nums. Again, we don't give arbitrary negative signs, and we can think of parentheses as dictating the order in which operations are executed, which means what we can do is we can start how we did in Q4 by generating a string or a list, essentially. I mean, a string is just a list of characters. But what we can do is we can generate a list where each element is either a number or an operation. And what a parentheses does is it combines, it essentially groups two numbers with an operation, because when you group two numbers in an operation, that will simply output another number. And so what you can do is you can replace those three elements of the list with a single element, which would just be that the two numbers and the operation in parentheses. You'll see what I mean later, but basically that's what we want to do, because parentheses can only dictate the order in which operations are executed, which means that we need essentially we need n parentheses, n sets of parentheses. So to solve the problem, we'll do the following. First of all, we'll generate all permutations of the n-1 operations, sort of like what we did last time, except n was set to 3. And then generate all permutations of nums. And it's important to note that when we're doing this, we are not allowed to repeat numbers, whereas with operations, we can repeat operations. We then want to generate all permutations of execution order for n-1 operations. Right? We have n-1 operations, but all the parentheses do is determine what order they go in. And so we need an execution order as well. And then for each configuration, which means a permutation of operations, of nums, and of execution order, we can generate an expression with parentheses and check if it evaluates the target, once again using Python's eval. And if it does, we should return it. So first of all, this is a helper function that will generate permutations with reuse, and we'll use this to generate all possible permutations of our operations. So it does this recursively, and essentially what it does is to generate all combinations of length n, we can take all permutations of length n-1 and add one additional element to the end. And so basically what that means is for every for n-1 permutations, we can essentially generate n more permutations by adding another element. So it might be sort of hard to envision, so maybe I can show you a visual. Let's say for simplicity we only have two operations, and we want to generate all permutations of length 3 with reuse. So what we can do is we can take all permutations of length 2, which I've listed here. So there are only 4 permutations of length 2. We can create 2 permutations per permutation of length 2 by appending another operation. So you can see here, plus plus, we can append plus or minus to generate these 2 permutations. Plus minus, we can append plus or minus to generate these 2 permutations, etc. And so therefore we have 8 permutations of length 3 with reuse, which makes sense because for permutations of length 3 with reuse, mathematically that would be 2 to the 3 permutations, which is 8. So this accounts for all of them. And by the way, when doing this recursively, the base case would just be to return an empty list when n is equal to 0. And when n is equal to 1, the only possible permutation is just the element itself. So now we need a helper function that will generate permutations without reuse. And we need this for 2 things. We need this to generate the permutations of our numbers, because we can only use each number once. And we can also use this to generate the execution order, because each operation can only be performed once when evaluating the number. So again, we do this recursively. The base case is if we only have one number in our list, then the only permutation is the number itself, obviously. And the recursive formula is basically what we do is we'll first remove an element from our list, or from our permutation, I should say, and then we can find all permutations of length n minus 1 without that element, and we can add the element back to each of these permutations. So in this next slide, I'll show you exactly what I mean. Let's say our list of nums is 1, 2, 3, and we want to find all permutations of length 3 with each element used exactly once. So first, we would need to branch into 3 different cases. First, we would remove the first element 1. So we would have a list 2, 3, and we will find all permutations of length 2, which is just 2, 3, and 3, 2. We do the same by removing 2 to get 1, 3, and 3, 1. And we would remove 3 to get 1, 2, and 2, 1. Then we take each of these permutations and we simply add the element we removed to the front. And we would generate, for example, in this case, when we had removed 1, we would generate 1, 2, 3, and 1, 3, 2. And we get all of our cases here. And so in total, we have 6 permutations when we are not allowed to reuse elements, which makes sense because mathematically, we should have 3 factorial permutations, which is equal to 6. So we have all of our permutations, good to go. Now we need a helper function that can generate a Python evaluable expression given given our three permutations. So we should be given our permutation of operations, our numbers, as well as execution order, which are the inputs to this construct expression function. And basically, what this does is it will generate a list where each element in the list is either an operation or a number, and it'll do this in an alternating fashion to create the expression. But then what it'll do is it'll iteratively go through the execution order. And depending on the order of execution, it will go to that specific operation and condense the string at that location. And what I mean by that is it'll take the operation, it'll look at the numbers adjacent to that operation, and it'll replace all 3 of those elements in the list with a single element, and that element will contain a parenthesized version of those 3. So in this next slide, I'll show you what exactly I mean by that. So let's say our inputs to this function are 5, 1, 6, 7. The operations are divide, add, and subtract. And then the order of execution is 2, 0, 1. So what this means is that first the subtraction should happen, and then the division should happen, and then the addition should happen. So our initial list would look something like this. This is what our expression would look like. But then iteratively, we'll go through the order. And so we say that we want operation 2 to happen first, which means that these final 3 elements of the list get condensed into one single element that looks like this, which is a parenthesized version of the instruction where we do 6 minus 7. Then we want operation 0 to happen next, so we condense the first 3 elements to one single element, 5 divided by 1. And when we condense an expression that has a division in it, we want to check that the element to the right of the division sign is not equal to 0. In this case, it's equal to 1, so we're good. For our next iteration, we want operation 1 to happen next. And so since there are only 3 elements left in this list, we combine all of them, and this is our final expression, and the function will know to return it. So now we can put it all together. And you can see by using our helper functions from earlier to generate permutations, we can generate all permutations of the operations, all permutations of the numbers, and the execution orders. And then we just use a triple nested for loop to go through every single possibility. And we use our construct expression helper function to generate a string expression, which we will then evaluate and check if it's equal to our target. If it is, then we return it. Otherwise, will return no solution. And that's pretty much it. That was a very long question, but thanks for bearing with me. It definitely, I definitely struggled a lot with it because I had no idea about Python's eval function, so it was very tricky. But I'd just like to make some acknowledgements before I end this video. Thank you to Professor Guerzhoy for the course and the final exam content. Also like to thank my lab TA, Ariel, for always being a great help throughout the course. And finally, I'd like to thank the individuals I stole my Beamer template from. But yeah, thanks so much for watching.